So we talked about some simple gas laws, and those relationships can be combined into one equation. So we saw that the volume of a gas was proportional to 1 over the pressure. The volume is also proportional to the temperature, and the volume is proportional to the amount of gas in moles. So we can combine those and say that the volume is proportional to N times T over P. So to make a proportionality into an equality, you have to add in a constant, a proportionality constant. So that's what the R is. So V is equal to nRT over P, or without the fractions, PV equals nRT. And so this is what's known as the ideal gas law. Some people call it PIVNERT. There aren't any vowels in there, but you could try to pronounce that. And R, that proportionality constant, is called the ideal gas constant. The value of R is going to depend on what the units are. Just like, the length of a piece of paper could be 12 inches, or if you express it in feet, it's 1 foot, right? So the number depends on the units that you use, and that's the same with the ideal gas constant. Typically, we use atmospheres for pressure and liters for volume, and so that gets us a value of R 0.08206 liter atmospheres per mole Kelvin. And those are very messy units, but those are just the units of the other quantities in this relationship. This is a slide showing the relationship between these different gas laws. What I'd like to show you is how you can derive all of the other gas laws from PV equals nRT. So if we write PV equals nRT, that's an equality, and if we divide it by the same thing on each side, then it's still equal. I'm going to call this P1, V1, N1, and T1. And let's say we're going to divide it by P2, V2. So as long as I do the same thing to both sides, it's still equal. But I know that P2, V2 is equal to N2, R, T2, because that's just another version of, or another statement of the ideal gas law. So what I'm doing is I'm taking one ideal gas law and dividing it by another one. One's on the top, two's on the bottom. And from here, you can make any gas law that you need. So obviously the R's are going to cancel out because they are constant. So R is equal to R, and so those cancel out. So let's see how we could make, say, Avogadro's law out of this. Yeah, question? Oh.
What's R?
R is the ideal gas constant. It's a proportionality constant.
Okay. Your
Pressure, volume, amount of gas in moles, and temperature. So Avogadro's law is when we have constant pressure and constant temperature. So if that's the case, then pressure 1 is equal to pressure 2, right? We're changing the volume of the gas, the amount of moles, but the pressure isn't changing. So pressure 1 equals pressure 2. Do we need to know what they are? No, because they cancel out. Oops, that's not what I meant to do. P1 and P2, at constant pressure, those are the same. Everybody okay with that? So I'm going to erase them because that makes things look better later. Well, if the temperature stays constant, then temperature 1 is equal to temperature 2. And the temperatures cancel out. Right? So I can erase those. What I have left is Avogadro's law. It doesn't look exactly the same as the way it was shown. We have to switch these two. V1 over N1 equals V2 over N2. That's how it was presented in the book, Avogadro's law. So you can do that, PV equals nRT divided by PV equals nRT, cross out all the things that don't change, and then you've got left the equation that you need. Yes? The constant is never going to change, R, but then the other things, it depends on the problem. Right, so for Avogadro's law, P and T are constant. If we were doing something with constant N and P, then we'd cross out the N's and the P's. So that would, we could do that over here, maybe in a different color. PV equals nRT divided by PV equals nRT. And we've got something where N and P are not changing. Well, the N's cancel out, and the P's cancel out, and the R's cancel out. And so V1 and T1 on the top, and V2 and T2 on the bottom. Now, this is not arranged exactly the same as it was presented to you, but that doesn't matter because you're going to rearrange it anyway, right? So if I'm going to solve that problem, I'm going to cross multiply here. V1 T2 is equal to V2 T1. And then I'm going to solve for the variable I need. So all you really need to remember is PV equals nRT. Divide it by itself. Cross off anything that's not changing. So we're going to do some problems with the ideal gas law. An 8.5 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and PSI of the gas in the tire? Now, this is an ideal gas law problem because it says ideal gas law at the top, right? But the problems on the exam won't be labeled like that for you. So sometimes we can read the problem and recognize, oh, there's nothing changing here. It doesn't say that the temperature's going up or that the gas is being compressed or anything like that. That's the clue that it's an ideal gas problem. But maybe you don't recognize that, especially on an exam when you're just not thinking very clearly. We can still take the approach of let's make a table, and once we get all the information, then we'll see what we need to do. So if we do it that way, I'm going to start making a table. Same way I did for the other ones. I've got 1 and 2. So the first thing I come to is 8.50 liters. Well, liter is a unit of what? Volume. So I'm going to call this column volume. And next I get 0.552 moles. And what letter do we use for that? N. N for number of moles. So that's N. And then I get 305 Kelvin. And I say, oh, that's kind. They gave me the temperature in Kelvin. That's different. That's the temperature. And those are all the numbers, right? I have nothing in this second row. That means I don't need it. Just scribble it out if you don't have a good eraser. Was making the table a waste of time? No, because it labeled everything for me. Now I see that I don't have 1s and 2s. I just have one set of conditions, so that means it's just the ideal gas law. PV equals nRT, because there's no 1s and 2s. What am I trying to find? The pressure. It says, what's the pressure? So, the ideal gas law doesn't have a fraction in it. So we can just rearrange this. I'm going to divide both sides by V. So the V's cancel out. And so I need N times R times T divided by V. So N is 0.552 moles. And R It doesn't say anything about R. R is a constant. I'll give it to you on the exam, but it'll save you a lot of time if you memorize it. 0.08206, and the units are liter atmospheres divided by moles times kelvins. And I'm not going to have enough space. I can just tell that already. So we'll start over down here. So times R, 0.08206 liters times atmospheres divided by moles times Kelvin. And the temperature, 305 Kelvin. And the volume, 8.50 liters. Now the units on that gas constant are messy, but they're actually helpful because they tell us what the units need to be on everything else. So when I look at this equation, I need to check that my units are going to cancel out. So here I have moles and moles. Those cancel. And kelvins cancel with the kelvins. And now on the top I have liters times atmospheres, and on the bottom I have liters, and so the liters cancel out. And I'm going to have the pressure in atmospheres. So now I can use my calculator. 0.552 times 0.08206 times 305 divided by 8.5. And most of these things have three significant figures. So 1.6253 atmospheres. So the pressure in atmospheres is 1.63 atmospheres. Anybody else do the math and get that number? Yeah. And then it also asks for the pressure in PSI. So I'm going to take my unrounded number and convert to PSI. I'm going to refer to the pressure unit table, and I'm going to do this in one step, PSI on top and atmospheres on the bottom. And the table tells me that 14.7 PSI is equal to 1 atmosphere. And so that's going to give me 23.892 PSI, which I will round to 23.9. Oops. PSI. Any questions? The question asks for two answers. To get the problem right, I have to give two answers.
So the test is going to be mostly ideal gas law problems?
The test will not be mostly ideal gas law problems. No, sorry. Here's another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? So let's say we recognize that nothing's changing and this is an ideal gas law problem, and so we're not going to make the table, we're just going to write out the numbers and identify them. That's a different approach. So 0.556 moles. What variable is that? N, number of moles, yes. Okay, and then it says a pressure of, what's the letter for pressure? P, capital P. The pressure equals 715 millimeters of mercury. And temperature, capital T, is 58 degrees Celsius. And when we see temperature and degrees Celsius in gases, what do? We change it to Kelvin, just immediately. So we're going to change this to Kelvin. 58 plus 273, 331. And is asking us to find the volume. So we're going to use PV equals nRT. And we're going to rearrange this cell for volume. So we're going to divide both sides by P. So to make this look nicer, I'm just going to, instead of crossing those out, I'm actually going to make them go away. Just rearranging the equation. And then I'm going to plug things in. Now, I've got N, P, and T. I don't have R. Well, R is a constant, and so if I don't remember what it is, I'm just going to go look it up. R equals 0.08206 liters times atmospheres divided by moles times Kelvin. I can save myself some trouble by looking at these units and looking at the units on my other numbers and making sure that they're going to work out. Moles is going to be fine. How about millimeters of mercury? That's not going to work. I need the pressure in atmospheres so the units will cancel out. It's easier to convert it before I stick it in the equation. So converting here, pressure conversions are always one step. I'm going to have atmospheres on top and millimeters of mercury on the bottom. 1 atmosphere is 760 millimeters of mercury. And that is exact. So 715 divided by 760 my pressure is 0.940. There's my 3 Sig Figs. I'm going to put 2 extras. Atmospheres. And my temperature's in Kelvin, so now I've got the correct units. So in my equation, I'm going to put in N, 0.556 moles. And R, 0.08206 liter atmospheres per mole Kelvin. And T is 331 Kelvin. All of that divided by the pressure, 0.94078 atmospheres. I check my units, moles cancel, atmospheres cancel, kelvins cancel. .556 times 0.08206 times 331 divided by 0.94078 equals. And this is going to be liters. So I'd round that to 16.1 liters. Yes?
So when we convert from 58 degrees Celsius to Kelvin, should it be 2 Sig Figs there, or should it just, are we going to keep it as 3? Or?
So that's a good question. So when we convert 58 degrees Celsius to Kelvin, what do we do about the Sig Figs? Well, following the rules for significant figures, when we add, we keep the same number of decimal places. So this had 0 places after the decimal point.
It's just weird.
I know it's weird.
Because you end up with more than what you have.
Exactly. When you add numbers or when you subtract numbers, you can end up with a lot more significant figures, or you can end up with fewer significant figures. And it's not something that you can just know. When you're doing multiplying and dividing, you can look, oh, well, you know, my smallest one has 3 Sig Figs, my answer is going to have 3 Sig Figs, great. But you can't do that when you're adding and subtracting. So because the Celsius degree and a Kelvin are exactly the same size, just keep the same decimal place. Now, Ideally, you would use 273.15. The book doesn't do that, and I'm okay with you leaving off the 0.15, but if you want to put it on, that's better. But yeah, the temperature can change in Sig Figs. And so if you're a person who just like hates significant figures, right, which is probably at least half of you, how can you kind of fudge an answer on this and know how many Sig Figs? Don't pay attention to the temperature. Just say, well, the temperature does weird things. I'm going to look at the other numbers. Which one has the fewest? I'll go with that, and you'll probably be right. Okay. The moles has 3 Sig Figs. The pressure has 3 Sig Figs. 715 is a whole number, but that doesn't mean it's exact. This one's exact, this relationship. Yeah. So we can't look at this 58 and say, oh, my answer's going to have 2 Sig Figs. Any other questions? So 16.1 liters. Determine the pressure in millimeters of mercury of a 0.133 gram sample of helium gas in a 648 milliliter container at 32 degrees Celsius. Yeah, things are escalating fast here.
So that must be a relationship between gram.
There must be a relationship between grams and moles. Yeah. So this is where, we're taking other pieces that we've learned and putting them together. And that's why when I said that chemistry is cumulative and it builds on itself, I wasn't joking. I was deadly serious about that. Because the dimensional analysis is just peppered all the way throughout the class. Unit conversions and the metric system it's not going to go away. So we can read this and say, well, I'm not sure what's going on. It doesn't look like anything's changing, though, because I don't have like 2 volumes or 2 pressures or anything like that. And then, of course, we have this up here. It says ideal gas law. So that's kind of a clue. Come on, pointer. There we go. Ideal gas law. So I'm just going to take these numbers and write them down. You could make a table. It's not going to hurt anything. So the first number I get is 0.133 grams. And does that match up with any of the variables in the ideal gas law? No, it doesn't. That's a mass.
Is there a relationship between ATMs and moles?
Well, we'll figure it out. So that's a mass. We don't know what to do with it. We'll just let it sit there and hopefully we'll feel better about something else. 648 milliliters. Okay, that sounds better. What's that? That's volume. Okay. 32 degrees Celsius. Temperature. Is Celsius a good unit for gas problems? No. We should convert this to Kelvin. Plus 273. And, we should be able to do that in our heads, but I'd rather not make a mistake that way. 305 Kelvin. And I'm trying to find, the pressure in millimeters of mercury. Yeah, we're going to need milliliters converted to liters, so we might as well take care of that right away too. Milliliters and liters. On the worksheet I just graded last night, I'm still seeing some people doing this conversion backwards. Okay, and then you get the answer wrong, and that's just really unfortunate. So milli is in the bottom. I'm going to write what milli means on the other side, 10 to the minus 3. So 1 times 10 to the minus 3 liters is 1 milliliter. We have used milliliters in lab now, and so you should have an idea of how big a milliliter is. It's a cube about how big? Hold your fingers up. It's like about this big, right? Little thing, a centimeter on a side, right? How big is a liter? It's half of a 2-liter soda bottle, right? We're all familiar with that size. So, are there 1,000 liters in 1 milliliter? 500 soda bottles would fit in something this big. No, that's ridiculous, right? But people do that with this conversion. So stop and think about it. Does it make sense? Because it's really easy to move the decimal point the wrong direction. So milliliter is a small unit. I'm going to a bigger unit. There's a bigger, smaller relationship here. The smaller unit has the bigger number. The bigger unit has the smaller number. That might help you avoid some mistakes. So this is going to be 0.648 liters. And we should get to the point where we can just do that conversion by moving the decimal point over. But make sure that you're confident which direction. Well, I've got volume and temperature, and I want pressure. So I'm thinking, well, ideal gas law, right? If I want the pressure, I'm going to divide both sides by volume. And the volumes cancel out over here. I've got temperature, I've got volume. I know what R is. 0.08206 liter atmospheres per mole Kelvin. What am I missing? I'm missing moles. And I'm given a mass. Can we convert grams to moles? Sure we can. This is helium. Where do we find the molar mass? Periodic table. So I want moles on top, and I want grams on the bottom. 1 mole of helium weighs 4.003 grams. And that's a small number, but that's okay. So I took the mass and I converted to moles. Because mass and moles are amount of substance, quantity of matter. One is by mass, or a weight, and the other is number of particles, and it's the number of particles that we need for gas laws. So now we can put all of these numbers into our equation. 0.03325. Wait, I lost a 2. Moles. And there's R. 0.08206 liter atmospheres per mole Kelvin. And temperature 305 Kelvin divided by the volume 0.648 liters. I'm going to make sure the units are okay. Moles cancel, Kelvins cancel, liters cancel. I'm left with atmospheres, which is not the unit that they asked me for. But I can do that. I can fix that up later. So 0.033225 times 0.08206 times 305 divided by 0.648 equals. So I get 1.2832 atmospheres. And the unit requested is millimeters of mercury. So I need to convert that. 760 millimeters of mercury is 1 atmosphere. So 975.29. 975 millimeters of mercury. Any questions? Yes. Yes. It's been kind of boring so far, right? They do all these P and V ones. But yes, sometimes we'll have to solve for N, sometimes we'll have to solve for T. Yeah. Any other questions? $976. I got $975. Interesting. So the answer that the book gives is 976, and I got 975. Column up. Is that something I need to be disturbed about? No. Because it's the last significant figure, and it's off by 1. Most likely what happened is, unlike all the other times, they used 273.15, and so this was 305.15, and that would make this a teeny tiny bit bigger. But we're going to say that's good. Now, a lot of my problems on the exams are multiple choice, and so for this problem, if this was multiple choice and the correct answer was 976, there's an answer 976, and there's a none of the above. Because you don't find 975, does that mean you choose none of the above? No. I try to avoid doing that to you because I think that's mean. But I have had people, I didn't do none of the above, and they can't find the exact number they come up with, and then they don't know what to do. Don't freak out. If it's just different in the last digit, it's okay because none of these things are exact. They're all measurements and there's uncertainty.